Now, in this previous lecture, we have studied the system response with the poles. Now we study the system response with the zeros. Now we have seen that zeros of the response affects the residue or the amplitude of the response component, but it do not affect the nature of the response. That is, it do not affect the response to be exponential, damped, or the sinusoidal. So in this case, what we do, we add a zero in the left half plane and then to the right half plane, and we analyze the effect of that and reach to some conclusion, as we have done in case of poles. Now let us consider a system where the poles of the system are at -1 plus minus j 2.828. The poles of the system are at this point, and we consecutively add zeros at -3, -5 and -10. It means that we add these terms in the numerator because zeros are at the numerator. Now the response of this is plotted, which is shown in this figure. Now from this we observe that this first line is the line with no zero. Then after that we get the line with -10 near that. Then we have the -5, and after that we have -3. So we see that closer the zero is to dominant poles, the greater be the effect on the transient response. That is, it is closer, -3 is closer, so its effect on the transient response is greater. And as we move away from the dominant poles, as we are moving away from the dominant poles, then response approaches to that of the second order system, as we have seen in case of -10. As it is moving away from that, the response is more and more towards the no zero response. Okay, so this expression can be reasoned through a partial fraction expansion. As we have seen in the partial fraction expansion, if we assume a group of poles and zeros far from the poles, the residue of each pole will be affected the same by the zero. That is, the relative amplitude remain appreciably the same in both the cases. Okay, so let us consider a transfer function Ts in which one zero is there and two poles are there. By using the partial fraction expansion, we found out the value of A and value of B. Now in this case, if zero is far from the poles, that it means that this A is very far from B and C. In that very case, this A is large compared to B and C. The value of the A is large as compared to B and C, so other components are negligible. So finally, using that, we get the equation as A divided by S plus B and S plus C. So in this case, A is nothing but a simple gain factor. What is A? So it is nothing but a simple gain factor, and it does not change the relative amplitude of the component of the response. So A in this case is simple gain factor if it is far away from these dominant poles, and it does not affect the relative amplitude of the components of the response. Now, looking differently, we can explain it like that. Now, if we add a 0 to the transfer function, yielding s plus a into ts. So, it is simply the multiplication of this with the transfer function, that is s plus a into cs, and it can be divided into two parts, that is scs and acs. So, in this case, we will see that the response of the system consists of two components: the derivative of the original response and scaled version of the original response. So, this is the derivative of the original response, and this is the scaled version of the original response. If a, the negative of the 0 is very large, the Laplace transform of this response is approximately ACS. So, if this A is very large, then the total Laplace transform is equals to ACS, or the scaled version of the original response. That is, A is large, then the Laplace transform would be scaled version of the original response, ACS. Okay. If A is not very large, the response has an additional component consisting of derivative of the original response. A is not very large, then we have SCS. That is, response has an additional component consisting of derivative of the original response. As A becomes smaller, as this A becomes smaller, okay, the derivative term contributes more to the response and has greater effect. So, this contributes more to the response and has greater effect. So, for the step responses, as we have seen, the derivative is typically positive at the start of the step response. Thus, for small values of A, we can expect more of overshoot in the second order system because of the derivative term, which is additive around the first overshoot, as we have seen here. Okay. So, this idea is clear that if A is not large, then there is more overshoot, as we have seen in case of -3 as compared to -5 and -10, because this derivative term will be more as compared to the scaled term, and as a result we get this type of response. Okay, I hope you understand. Now, the case that we have discussed, in that case, it is this 0 is on the left side of this. It is on the left side that we have discussed. Now, let us assume that we have placed a 0 on the right half plane. That is, we have placed the 0 on this right half plane. Here, somewhat we have placed the 0. Now, if we place the 0 in the right half plane, then we see that derivative term, which is positive initially, it was initially positive and it gives the some overshoot. Okay, will be of opposite sign from the scaled response. So, this is negative from the scaled response, and if the derivative term is larger than the scaled response, then that is, this term is larger than this term from the scaled response. The response will initially follow the derivative, but in the opposite direction from the scaled response. That is, it is derivative in the opposite direction. Okay. Now, which can be seen from this plot, that is derivative is in the opposite direction and this negative is there. Because of that, and since it is near the axis, and as a result this derivative term is dominant and it is negative as compared to the scale term, and as a result we are getting negative here. As the sign of the input is reversed, okay, notice that the response begins to turn towards the negative direction even though the final value is positive. So initially the response is negative even though the final value, steady state value, is positive in this case, and a system that exhibits this phenomena is known as non-minimum phase system. That is non-minimum phase system. For example, let us suppose that we have a motorcycle or airplane was of the non-minimum phase system. So it means that it will initially move towards the left when we command it to the right. Okay, nice. So from the practical point of view, that non-minimum phase system should be avoided. Otherwise, if you want to move towards the left, then first you have to move towards the right and then to the direction as clear from this graph. Okay. Now we discuss the pole zero cancellation using the residues. Now let us suppose that we have a three pole system in which one zero is there. Okay. And if the pole term, that is this term, cancel out with this zero term, then we are left with only k divided by s square plus as plus b. From another perspective, we will see that if the 0 at minus z, okay, 0 at minus z is very close to pole at P3, 0 at minus z is very close to pole at minus P3, then we can show that residue of the exponential decay is much smaller than the amplitude of the second order response. That is, residue of this exponential decay is smaller than the amplitude of the second order response, and we can neglect it. Now it can be explained with one example. Now let us consider a function, transfer function, in which we have to show whether the pole zero cancellation is valid in this case or not using the residue. Okay. Now let us suppose the transfer function is given by 26.25 into s plus 4 divided by s into s plus 3.5, then s plus 5, and then we have s plus 6. When we by partial fraction expansion, we are getting 1 by s minus 3.5 divided by s plus 5 plus 3.5 divided by s plus 6 and minus 1 divided by s plus 3.5. Okay. Now from this figure, from this equation, we see that the residue of the pole at minus 3.5, which is actually closest to 0 at minus 4, is equal to 1. Okay, that is the residue of the pole at minus 3.5, which is closest to 0 at minus 4, is equal to 1. We can say that it is not negligible as compared to other residues. So the second order step response approximation cannot be made for this function, and cannot be made for this function. This is how it can be done with the residues, that is pole 0 cancellation with the residue. Now let us consider another example in which in the this denominator, instead of 3.5 we can use 4.01, that is we have used 4.01. Now after having this partial fraction expansion, we get this. Now the residue of the pole at minus 4.01, which is closest to the 0 at s equals to minus 4, is equals to 0.033, about 2 orders of the magnitude below any of the residues. So we make a second order approximation by neglecting the response by pole at minus 4.01. So finally our response would be 0.87, that is 0.87 divided by s minus 5.3 divided by s plus 5 plus 4.4 divided by s plus 6. Now the final response in the time domain can be obtained by inverse Laplace transform, that is equal to 0.87 minus 5.3 e minus 5t plus 4.4 e minus 6t. Okay, so in this way we can neglect that term, that is we can cancel the pole zeros by using the residues. So in this lecture we have studied about the use of the poles, use of the zeros, that what is an effect of the zero on this response of the system, that is transient response of the system. I hope you understand the topic well. So I think you understand well about the placement of the zeros on the left hand and the right hand of the plane, and how it affects, how this slope is affected from the left hand to the right hand, and how the minimum phase response is also obtained in that very case. Now this is very important from designer perspective, that if he wants to approximate the system to the simplest second order system, then he can see what are the poles and zeros, and then after that approximate it, so that it is easy for analyzing any system. So thank you very much for this lecture. Thank you.